Hey class, today I'm going to be doing a review for lecture 29, which is the lecture of heat, energy, and work. So let's get this open. All right, so to begin, we started talking a little bit about thermodynamics, and we need to make sure that we can know what thermodynamics is. It is to understand and predict the amount of energy available in a chemical source. That chemical source is going to be our system. Now, the first law of thermodynamics means that the total amount of energy in the entire universe is going to be constant. What that means is that in the entire universe, when energy is lost in one thing, that energy needs to go somewhere and something else will gain that energy. So that means that all of the energy in the entire universe is constant, just like the consistency of mass, where mass never changes in the entire universe. Energy is not created nor destroyed. It's always the same. Now, when we're talking about change in energy, this little delta that means change, what this means is that the change in energy of the universe is always going to equal 0. So when energy of something is negative, energy of something else will be positive, and they will cancel out, and it will be 0. So there are 3 different types of energy, especially those that we talk about during this class. We've got radiant energy, kinetic energy, and potential energy. So we're going to focus a lot on kinetic and potential energy in this lecture that we are reviewing. And first, we're going to talk about it on an atomic level because this is chemistry and we're talking about how they're interacting with each other. So first, the potential energy on an atomic level is the chemical potential energy. That just means the positioning of the different atoms, like the bonds between them and the intermolecular forces holding different atoms together. That holds a potential energy. And when you break a bond, you are putting energy into it, and when you form a bond, energy comes out of it. Now, with kinetic energy on an atomic level, it has to do with the motion of the atoms. So there's translational motion, which means that the atom's moving from point A to point B. There's also rotational energy or motion, which means that the atom is just spinning in place. And then vibrational just means, like we can see right here, it just means that the atom is kind of stretching in one direction and another. So it's kind of wiggling in its same location. Now with all 3 of these all moving together, while it's kind of spinning, kind of vibrating, and kind of moving, those are all of our kinetic energy of our molecule. And the temperature of our system is proportional to the average kinetic energy. So if everything is moving a little bit faster, it's a little bit hotter. Okay, now we're gonna go from talking about potential and kinetic energy to talking about internal energy of a system. So especially on a molecular level, the internal energy is the amount of kinetic energy there is in the system plus the amount of potential energy that we have in our system. So the units that we're going to be using is primarily we're going to use joules. And then we're also, especially when we start talking a little bit more about gas, we're going to talk about liters times atmospheres, which 1 liter atmosphere is 101.32 joules. That is on the chemical equations sheet, so we don't have to memorize that. And then we're also going to talk a little bit about calories. So a calorie is 4.184 joules, and that's a lowercase calorie, not the calories of us while we're eating. And 4.184 joules is the exact amount of energy that you would need to put into 1 gram of water to raise that 1 gram of water 1 degree Celsius. Now, a little bit later, we start talking about enthalpies, and that is when, we start talking about specific heats, and that is when especially this unit comes into play, is when we're talking about the specific heat of water, and when we're talking about the specific heat of other things. That's when we start talking about how much energy is required to raise 1 gram of anything 1 degree Celsius. So 1 calorie, that's a good unit to remember. Now, as far as how energy is transferred, we use 3 different types of systems, especially in this class. I think most of what we're working with is open systems. but there are isolated systems, which means the energy just remains within the system, or within, the entire system. So no energy is going to go out to the surroundings, but also no matter is going to go out to the surroundings. So depending on the change of the energy inside the system, the pressure could go up within that system, things like that. With a closed system, that means that only heat energy will be leaving or going into it. So that means that the amount of matter that is within that will always stay the same. So the pressure could go up or down, but the heat can leave. So that means if something starts to heat up its surroundings and it's giving off heat, the system itself will cool down, which I'm going to review a little bit more in a second. But then the opposite is also true, that if the temperature goes up, then the surroundings will start to kind of cool down and the system will be heating up. Now, with an open system, that means that energy can go out, but also matter can go out. This is especially important with most reactions that we work with in this class. From what I've seen, normally we want the pressure to be constant. So what that means is that some vapor can be leaving so that the entire pressure of our system is the same as the atmospheric pressure around our system. That will get really useful, especially when I review a little bit about what enthalpy is. Now, so the system is what's kind of inside the box. It's what we're focusing on. The surroundings is everything else. So we have a couple of questions that I've seen on problem sets and on SmartWorks where we're supposed to name what's the system, what's the surroundings. Pretty much the system is just exactly what we talk about. If it's ice cubes in a cup, we're talking about the ice cubes in a cup. If we're talking about the temperature of a liquid, the system is the liquid, the surroundings are the air. And especially one that's been really tough is whenever we're talking about water on a person evaporating. When that water is evaporating, the water is the system and the person who is cooling down is the surroundings. So we're just talking about that water, like the sweat on the person's forehead. We're not talking about the skin of the person or the person themselves. Okay, so state functions, this one was a little tricky to understand for me at first, but pretty much what a state function is any unit that we can put this little delta symbol in front of. A state function is where it doesn't really matter, where it doesn't really matter a path that we take to get from one place to another. All that really matters is how much we had at the beginning and how much we have at the end. And we just measure just the change in that. So measuring the total internal energy is like super impossible, especially in this class. So what we try to do is just measure the change in internal energy, just the final amount of internal energy minus the initial. That difference, it's a state function. We just use that number. Now, some examples of state functions that I've seen on problem sets and on SmartWorks is, so like starting at the top of a building or at the bottom of a building, ending up on the top floor, like your altitude, it doesn't really matter how you got there, if you went up the stairs or if you went up the elevator, you just take your final location minus your initial location. The difference between that is how much altitude you gained. And then with thermodynamic systems, we talk about volume, pressure, internal energy, and temperature. All of those things are state functions. So it doesn't matter how our temperature fluctuated. We just care about where we were in the beginning and where we were at the end. Things that are not state functions include Q and W, which is the heat transfer, as well as the work done on or by the system. So when we start talking about internal energy, the change in internal energy are these two things that aren't state functions, our Q and our W. Just like I said, our Q is the transfer of heat energy. So that means that as energy is put in or energy is taken out of our system, that is our Q. Now W is our work being done on or by the system. W can be calculated using force times distance. And the energy is the capacity of the system to do work or to transfer heat. So when we have that internal energy, that means it can either do work on its surroundings, or that means that it can release that energy in the form of heat. Now, W will come along a little bit later in our review. And that one, we're going to start talking a lot more about gases with that. But Q is something that we're going to talk about a lot. And Q is pretty easy to calculate. Normally that'll just be in like kilojoules or in joules, and it just tells you how much energy was put in or how much energy was taken out in the form of heat. Now, when we are talking about putting these things in and taking things out, we need to distinguish the difference between an endothermic reaction and an exothermic reaction. So an endothermic reaction is when the heat is being transferred to the system by the surroundings. So when we're given Q, that means that Q will be greater than 0. It'll be a positive number. And so that means that energy needs to be put into the system in order for it to work. So that means heat needs to be put in. Some other form of energy just kind of needs to go from the outside to the inside of our system. And that means that Q will be positive for our system. Now, if it's exothermic, heat is being transferred from the system to the surroundings. So that means that the energy will be going from our system outwards towards the surroundings. And what that means is that the heat of our system will go down because it's decreasing. That's why it's negative, but everything else will be receiving that heat. And so that's what it means when it's exothermic. Now, similar to endothermic and exothermic reactions, we can talk about work, how when work is being done on the system by the surroundings, so the work being done on the system, then it's kind of receiving the work, so W will be positive. But when work is being done by the system on the surroundings, it's going to be negative, which means that kind of the amount of work is going down within our system because we're kind of giving that energy out by like increasing its volume and pushing on the air around us. That'll get a little bit more understandable when I talk about gases. And then again, the way we calculate internal energy is Q plus W. Okay, so when we're talking about endothermic and exothermic reactions, it's really easy just to realize how phase changes go. So if we're going from solid to gas, so pretty much the temperature of our system is going up, that means that Q is positive. So that means that the temperature from outside things is going into it. And so then it's going to change from one phase to another. It'll change from a liquid to a solid, from a liquid to a gas, or from a solid to a gas. Now, this is a good example with the sweat on the face thing we talked about, where if you have sweat on your forehead and that sweat is evaporating, that means the heat from you is going into the water and then the water is changing its phase. So it's endothermic, even though you will feel a little bit colder, but you are the surroundings, you're not the system. So while the temperature is going down on the surroundings, so while your temperature is going down, the system, the sweat's temperature is going up and it changes to a gas and floats away. Now, the opposite is true with exothermic, is that when you're going from a gas to a solid, anywhere in between, you're cooling down. And when the system is cooling down, that means heat is coming from the system and the things around it are warming up. Okay. So now when we're talking about gaseous work at a constant pressure, so what happens is our W is equal to negative pressure times the change in volume. And then we need to make sure that our units are in atmospheres and in liters when we're talking about pressure and volume respectively. Now, if the change in our volume is positive, so that means if the thing is getting bigger and kind of pushing away the air on the outside, just like this balloon, you see it's pushing against the atmospheric pressure. That means that W is going to be negative. And that is because the work is going on the outside things. So it's spreading out, which means the amount of work energy that we have within our system is kind of going down. So it's going to the things around it. But if the change in volume is negative, so if our volume is getting smaller, like it's getting compressed, that kind of raises the amount of work energy done on our system. And so that means that W is going to end up being positive. So when our work goes from the system outwards, it's negative. When the work comes from the system onto, or from the surroundings onto our system, it's going to be positive for our system. Okay, so now we do a lot of calculations, especially while we're working with gases where we're doing the internal energy. And so like we said at the beginning, our internal energy is equal to the amount of heat energy plus the amount of work energy. Now we can plug in negative P delta V, or the change in volume times pressure, for that W. So that means that our change in internal energy is equal to the amount of heat energy put in or taken out minus the pressure, the external pressure, times the change in volume of our system. So we have a lot of practice problems with that unit that we do, where we have to take, let's say, a balloon, and it says this amount of energy was put into the balloon, and then the balloon increased from this size to this size. What is the total change in internal energy? When that happens, what we need to do is take the pressure, the external pressure. So for example, if we're on a beach, it's 1 atmosphere. We plug that in for P. Change in volume, let's say the balloon goes from 1 milliliter to 10 milliliters. We take the final 10 milliliters, we subtract the initial, which is 1 milliliter, and we plug that in for our change in volume. So that would be 9 milliliters, because 10 minus 1 is 9. And then for Q, we just plug in the amount of heat basically that it says it puts in. Like, let's say it absorbs a certain amount of kilojoules from the sun. Then we plug that in for Q. And then we need to make sure that the units are the same. So this is when that the units that we talked about at the beginning is important, because when we're doing P times delta V, that's when we're working with liters atmosphere. But we need to transfer it to joules because generally Q is given to us in joules. So what we're going to do is we're going to plug in our digits for P delta V, and then after we solve for that, we need to transfer that to joules, and then we can use Q, which is going to be in joules or kilojoules pretty often, minus however many kilojoules or joules we have from our P delta V, and that'll give us the total internal energy. Now, enthalpy is kind of a really confusing thing at first, but we just need to remember enthalpy is the total energy of the system, the total energy change pretty much. So it's the internal energy that we have, so this E, and it can be delta E, plus the energy needed to push away the surroundings. So our enthalpy is the internal energy E plus PV. So the change in enthalpy is, so the change in enthalpy, our delta H, which is what we use a lot, is the change in internal energy plus the change in pressure times volume. So what we can actually do here is let me get this set up. What we can actually do is, so we have our change, oh, come on, draw. Our change in enthalpy equals our change in internal energy plus our change in pressure times volume. Now what happens is, if we kind of simplify this out according to the other things that Dr. Mortensen talked about, our change in internal energy is just Q minus P delta V. But then we need to finish this equation, so we're adding our delta PV. Now that change, that delta, is going to be the same, because P times V is always the same, and then that change would then be the same. So we could actually cancel these two things out, but only under one situation. That is if our pressure remains constant. So what kind of happens is, let's say that we have a graph of our pressure times our volume, and then we just pick a random point on that graph. So we are at this amount of volume and we're at this pressure, and then our system changes and it goes over to this volume and this pressure. Because of these deltas, we could measure these things for this point, the change between pressure from this point to this point, and the change in volume from this point to this point, and it wouldn't matter what route we took. However, Q and W can kind of be changing up. So if we like went that route from this point to this point, that is some amount of energy put in or taken out from our system. Well, if we then go back to the original point, we might take a different path and go back to our original point. Well, the change in pressure from this point all the way around back to this is just 0 because we're at the same spot. Change in volume is the same. It's just 0 because we're at the same spot. Change in internal energy, it's the same because we're back at that exact same spot. However, this space in between these two paths that we took shows us Q. It shows us what our heat is. So that area will change. We could start at this point and have only 5. Our Q could be 5. Well, then when we go around the area of this might be 2. So the next time we get back, it might be 7. And then the time after that, it might be 9 and then 11. So what we can do is we can actually make the pressure constant. And if we make the pressure constant, then as we change from our volume, the pressure remains the same. And then we can go from this point all the way to this one and back, and we're stuck on the same path. We can't change up that path because we can't change our pressure. So what happens is the area of that all of a sudden becomes 0. And so if we keep this at a constant pressure, then they cancel each other out. And at a constant pressure, our change in enthalpy is equal to our heat. Now that is one of the hardest things for us to understand, but as soon as we can just accept the fact that our change in enthalpy is equal to, here, let me get back here. As soon as we can understand that our change in enthalpy is the same as our Q, we can really begin to understand enthalpies throughout the rest of the class. Enthalpy then becomes pretty much the same, our change in enthalpy becomes pretty much the same thing as Q. And so then when we start talking about if our change in enthalpy is positive or negative, we can tell whether our reaction is endothermic or exothermic. Because if delta H is negative, that means that Q is negative. And when Q is negative, that means it's giving off energy, which means that it's exothermic. So that means the system's cooling down. The same with if it's endothermic. Energy is going into it. Our change in enthalpy will be positive and it'll change from a solid to a gas. So that is pretty much everything that we talked about during this lecture. And I hope that I was able to kind of clear up a couple of things. But that is it. Thank you guys all for watching.